मस्का मारा
So, welcome.
anyway x है तो कोई फर्क नहीं पड़ता
Yeah,
है.
yeah, yes, yeah. So, welcome, Professor Ravi.
Thanks Partha, thanks for the nice introduction. Okay, so I'll basically be talking about predicting some atmospheric parameters. I think after the large scale or the huge talks that we have had from Dr. Mahapatra and also from Sachi, mine is more like a cottage industry. I mean, small scale, nothing big. Whatever we can do with a laptop most of the time. That's what I have been trying to do for quite some time. So, and this is a work which is with my student Karan Purohit and my colleague who is at Art Park. Art Park is a kind of a incubation hub for at IISc, and one of my other students, Ananya. So this is the overall view. I'll start with the predicting the Indian summer monsoon. Then we look at the seasonal mean using AI, how we can do that, and predicting fluctuations of rainfall at subseasonal scales, which I think, as those of you are familiar, is a much tougher problem. Seasonal is easier, but subseasonal is tough. And okay, I'll not be talking about the predicting rainfall at shorter scales, where the skills are even not much to talk about with AI. And finally, I'll talk about some new work that we are doing on predicting heat stress using AI models. So this is something which I think all of you are familiar with. That is the mean monsoon. Indian monsoon, as you all know, has a very rich structure. And there are areas where, does the pointer move there or it doesn't, is it? No, I just wanted a pointer. I thought if the mouse can move, but no, it's okay. Nothing much to talk about here at this point. So no, it's just that if the pointer can, if there is somebody online, it might be easier for them. That's all. But yeah, that's not a problem. So basically, it has a very rich structure. There are areas where you find that most of the time in monsoon season, this is where our action lies, which is in the central Indian region. There's a lot of rainfall happening, which we came to know only through satellites. That is at the what we call as Head Bay or the northern Bay of Bengal along the Myanmar coast. And there's also a region of high rainfall, which is the central equatorial Indian Ocean, and also, of course, on the Western Ghats. And there's a region where the rainfall is pretty low, that is in parts of northern, this is Marathwada, northern Karnataka, and parts of Tamil Nadu, which is basically the where you have what we call as a rain shadow region. And wherever the rainfall is high, the variability is also high. So it's kind of they kind of go together. So what we have done right now is we have developed models to predict rainfall for entire India for the entire season. And for also what's called as homogeneous regions, IMD has 5 homogeneous regions, which we also have looked at uh, developing AI-based models for that. And also for the early part of the monsoon and the later part of the monsoon. So first, why predict monsoons? I think I am kind of preaching to the pulpit. All of us know why. But the first statement, it's not like we are talking about the 1880s. Now we are talking of 2011, where who was then the president, or who later on became the president of India, he said that he seeks the blessings of Lord Indra to bestow us timely and bountiful rainfall. So that's the kind of uncertainty we had. And as an interesting aside, after that, uh, government of India decided that they should have a kind of a dedicated mission, which is called the monsoon mission, which kind of spent quite a bit, which kind of was extremely successful, I should say, where I think Dr. Partha is here. He was one of the guys who were instrumental in developing the models there. Before that, we didn't have proper numerical models. There were some models, numerical models, but on a sustained basis, forecasts at different scales that could be done with the monsoon mission. So these are the other details. I think I will not go into that, like 70% of our needs and, of course, uh, let's say food and also GDP. What I would like to point out is, that when you are talking of areas, periods of high rainfall and low rainfall, excess and deficit monsoons, or as IMD puts it, if you are getting this is the rate of food grain production, and this is the rate of GDP production. If you are having a drought, then the reduction in GDP is much higher as compared to supposing you are having an excess rainfall year. You don't get that kind of the same kind of increment that you would expect. You would expect that if this was plus or minus 2%, it should be on the same side. The problem is that the droughts have a bigger effect, the excess don't have, and that's partly because of the reason that maybe we don't have a good enough model to predict monsoon, at least on the seasonal scale. So let's say if we knew it well in advance, that, okay, you're likely to have a reasonably good monsoon, maybe you can even give that information to the farmer and say that, okay, it's likely to be a good monsoon. Maybe you can invest more, because they don't want to invest and then kind of lose that money. So that's the loss. It's a big loss for them. So because of that, the lack of information may be one of the reasons why you're not getting the same kind of an increment when you have an excess monsoon as compared to a deficit monsoon. And that's one of the things which came out from one of the studies by my guru, who unfortunately passed away recently, Sulochana Gadgil. And they found that was a major result that they said, but which kind of always been the fact that if you can build good models, and today with AI being useful, we can see if we can do better models than what we can get with numerical models. I mean, this is not to say that numerical models are not relevant. They are more relevant than any. But if you're looking at a targeted kind of a forecast, then AI could give you a targeted, let's say if you're just looking at one number, which is the All India summer monsoon number, then it's possibly that the AI models could be able to perform better than, let's say, the numerical models. Okay, sometimes, the specter of a drought is more dangerous than the drought itself. So government is always very hesitant to say that it's a drought, because, it kind of leads to all kinds of chain reactions. Let's say some people may kind of, let's say, even in the international markets, if they know that, okay, India is going to have a drought, then the food grain commodities and other commodities might shoot up. So they are very hesitant. Of course, now the data is available everywhere, so they have information about droughts, but generally they are a little more hesitant to talk about droughts, which is why if you look at most of the forecasts, I think only once in its history has IMD stuck out its head and said it was a drought, and it was a drought. I think that was a very unique case. I don't remember which year it was, but no, 2002 was a disaster. They couldn't. I mean, they said it was a near normal or an excess monsoon, and it was a disaster, and no model in the world could do it. And that's when I think it became more, that's when people woke up and said, yes, you have to have better models to do forecast. And as time evolved and as AI came into picture, now people are also looking at using AI at different scales. I think so. It should be. I mean, both numerical models as well as AI-based models, at least on a seasonal scale, they are doing better. The accuracy might be kind of varying, but at least you are going to get a strong signal, both with, yeah. I mean, that year, I think it was a very interesting year where there was no real large-scale signal. If you look at the beginning of June, everything looked nice till the third week of June, and suddenly it kind of went into, it's like, I would rather say that, RCB, Royal Challengers kind of usually have this kind of a thing. They suddenly collapse, and so that's what happened to the monsoon. It just collapsed. Yeah, we could. I mean, when we looked at hindcast, we could look at some of the extremes, and we could predict it, yes. With AI models, you are able to, and even with some kind of accuracy, even with numerical models, we would be able to do it. Yeah, sure. Well, I mean, okay, slightly tongue-in-cheek, I can't do time travel. So I do what we call as a hindcast. That is, I say that, okay, I say that I have conditions for, let's say, 1st of May 2002. I don't have any other information. Then I do the prediction based on the conditions then. So that would be the kind of thing which we call as a hindcast. So there is no further information that you're giving. You're not saying that, okay, you know that it's a four. Other than the fact that you already have the information, you're not going to give it any additional information and see if it's able to capture a drought or an excess. Okay. Okay, so this I'll skip because I think I'm also running out of time. And basically everywhere, when we are talking of monsoons, we are for agriculture, water resources, disaster management, everywhere, using, monsoon information about monsoon at different scales is required. So I'll skip this slide for the lack of time. And we have used prediction of the mean monsoon using, and right now it's not state of the art, but what's called as a stacked encoder, which is we used it for the entire Indian monsoon region, which we call as the ISMR. And also for the season, we attempted to predict over the homogeneous regions and also for the early and later part of the monsoon. And the technique we used is called as the stacked encoder, which though not the right now the state of the art, but what we did was in the early part of the previous decade. And if you want to look at it, you'll find that even today, if you look at GraphCast, it has an encoder, it has a kind of a regression model and a decoder. So the same architecture, what we looked at conceptually is what we have used. And so it's a encoder regression classification decoder approach. So, and at every stage, we used automated feature learning. That is, we use the encoder to kind of do a dimension reduction, picked up the major features, then kind of looked at it, the target, which was the ISMR, and see whether there was a good relationship between those kind of identified predictors, identified features, and pick them up and use them for further forecasts. So this is the kind of flow chart that you're going to look at. The input is, we used sea surface temperature, sea level pressure, and winds at 10 meter. And we did some pre-processing, which is fairly standard. Then we used the stacked encoder decoder kind of a thing. Then used a post-treatment of thresholding of weights. And after that, we went to prediction. At this stage, you could either do a classification or you can do a regression. At that point, everything is the same. And either use a classification model or a regression model. So between the two of them, we chose and said, okay, we can use it for either classification or prediction. So this is the broad features of the stacked encoder decoder that we have done. And these are more details of it, which if somebody is interested, they can take a look at it. And I'll skip it for lack of time. And as far as it's basically unsupervised learning when it comes to an encoder. It's kind of picking up the features on its own. We are not doing anything. And once you have done multiple layers, you are taking the features which are predicted and then kind of targeting it with which is the Indian summer monsoon, and then building up the regression model. So that's in some sense. And the inputs are from NCEP-NCAR reanalysis, this was done in the late 20s, 19s and 20s, when the best data we could get was the NCEP-NCAR reanalysis. Today, we are trying to redo it with ERA. And instead of encoder decoder, we want to see whether we can kind of get better results with CNN, but there's a work in progress. Nothing from NWP. In the NWP is what we get is the reanalysis, which is basically a data assimilation system. It creates conditions that, like on a delayed mode, you get that data and you use that as input to your right now, we used SST, the sea surface temperature, the sea level pressure, the winds, and heights at geopotential heights at different times. Okay, I think somewhere I have put it. It's, I think, since NCEP-NCAR starts from about 1940s or 1950, I think 48 onwards. Oh, it's there, sorry. In 1948 to 2000 was a training period, and the independent testing was 2001 to 2014. Yeah. No, it was only from June to September. And it was not just June to September. We took data from previous months also. Let's say previous 6 months we could take. We would take and see, yeah, 6 months data. Or actually 1 year. Because I'll show in one of the later slides, even as early as the August of previous year, you could get a fairly good prediction of the Indian monsoon. Just using, I think, only sea level pressure. I think we found that it was giving a fairly good prediction. Yeah. Either a classifier or the target is the Indian summer monsoon. So you are going to predict or classify based on the Indian summer monsoon, which is IMD data. Sure. No, this is the NCEP-NCAR reanalysis. Reanalysis, standard reanalysis. Huh? No. We are not using any numerical model. The only place you are using it is, the data assimilation system is based on the numerical models. You kind of pick data from all others in a delayed mode, run it through the data assimilation, which includes a numerical model. That's the only place where you're using a numerical model. No, the domain, it's from various regions of the world, which is where, we took the entire globe, and that's where we did the encoder, and it could pick up features for various variables. I think I can skip this one at this point. Yeah. So after, I think 3 levels of encoder, based on, for sea surface temperature, these were the major regions which we identified as the input predictors. And for sea level pressure, these were the variables. And for U wind, these were the variables that we had used. Okay. So the regions are coming from, let's say if you're looking at a predictor at a particular level, they are kind of they're geographically separated also, but they are kind of becoming a single feature, which they are going to be used in this thing. And the information was coming from different layers, and we found that the deeper layers in our encoder contributed more as compared to the shallower layers. So this is the prediction. And we found that sea level pressure provides a good estimate of the seasonal mean as early as the August of the previous year. So supposing now I know that August of this year is there. So at least I'll have some information, which is that if you look at sea level pressure, it's using August from the previous year and getting a correlation of about 0.8, which is, at least as a first cut, as a prior information would be a useful thing for us to look at. And of course, these are the various combinations that we have used. And these are the errors that we are getting. So if you are looking overall, we find the combination of sea level pressure and sea surface temperature provides the best prediction. And if you're looking at comparing with numerical models, I'm also a numerical modeler, so it doesn't feel nice to say that, okay, it's outperforming it. But yes, the fact is it is doing better than that. And but today I should say that the latest work from the monsoon mission coupled model is getting a correlation of about 0.72, which is kind of comparable to what we are getting with AI. What was about at 0.55 has now jumped to 0.6, which is basically there's been a lot of work that has been done into improving the models. And that has kind of fructified from going from 0.55 to 0.7, which is a big jump when it comes to a coupled model. See, CMAP is a free run. I think even Shuvimal will say that once I have started my CMAP model, it starts sometime at 1880 with some condition of some CO2, God knows what. And then you spin up the model and let it run, give its own climatology. So year for year comparison, you will not get. In a statistical sense, you will be able to say that, okay, it may have the right number of droughts, it may not have the right number of excess years, but even the seasonal pattern of the monsoon itself is a problem with most of these CMAP models. We could do that, but it's again, somebody could give it a try, but we thought we'll go with pure data and then, or the proxy to pure data, which is reanalysis. Actually, if you go by meteorological things, you have IMD rainfall, which is one of the best curated data sets starting from 1880 to today. That's one of the longest data sets you can think of. So this is about the best. And having seen those models behave, I have my own doubts about how well they are able to resolve. There are serious problems within models. Of course, they are very important when you are going into the future because that's the only thing which you can use to see what the future is likely to be. So, but if you're looking at predicting the monsoon on a year-to-year basis, I'm a little worried. I would rather go with data rather than with civic models. And here's the comparison with IMD's. They still use statistical models, and of course, a combination of their models. Finally, they will give some forecast. So you can see that the errors are much lower as with our technique as compared to what the IMD's LRF is giving. And this is for the early and later part. I think the technique is the same encoder technique, but we did it for June and July and August and September, the early part of the monsoon and the later part of the monsoon. And here are the regions from the encoder. The one on this is for the predictors for, we used only sea level pressure and sea surface temperature for that. And these are the regions which we kind of got after which kind of contributing to the forecast. It's very similar to what we had done previously, so I'll kind of skip this. But what I would like to say that, okay, the forecast for early part is around 6.1%, which we could do it in April, with a standard deviation of about 12%. There is no equivalent, at least at the time when we did. I don't know whether they have an early June, July forecast. Do they do that, Partha? Any technique they use for the first 2 months or the later 2 months, they do it for August and September, but they don't do it for June, July. So we found that the error was about 6.1, which is fairly comparable, and error of 4.9 in late March as early, with a standard deviation for the later part of was done.
I have one small question.
Sure.
When this SST, what we find, there is a climate change signal in decadal, in the last decade, the rapid warming, wind sea and tropical equatorial Indian Ocean. So how that feature is assimilated in this training period, or
okay,
it is not
done, let's say in about in 2017 to 2018 period. So if there is we are again redoing the exercise. So I guess that information. So again, there will be other patterns which it will be. If there is a different pattern, that will also be captured in it. So and I hope that if the pattern is very different. For example, we know that in the 70s there was a decadal transition, mid 70s. Suddenly things changed. Some people think it's something happened in the Central Pacific. Some people think that it's part of climate change. But there are various factors which come into picture. But it has been able to capture, even with that kind of a transition, when you're looking at data from 1940, 50 onwards, whatever changes we found, it's been able to capture it and able to give a fairly good prediction for the later part. Of course, we use it only the training part. We didn't use it in the testing part. So this is for the homogeneous regions of India. IMD classifies it into different homogeneous regions. This is the, I think, Northwest India, Central India, East and Northeast India, and Peninsular India. So we kind of built models for each of them. And they also do forecasts using statistical techniques. And here's the comparison. For Central India, we could get an error of about 4.1%. Again, the same technique, so I'm not repeating the details. For Northeast India, you could get it for 5.1%, and for Northwest India, it was 5.5%, and for South Peninsular India, it was 6.2%, which is reasonable. And if you compared it with what IMD gives you, you can see that it's able to do it much better than what our proposed model does it better than. I think they have basically a kind of a regression model. Power regression model is what I remember it. Okay, so far so good. We were doing fine. So now we'll go to a stage where things are not so fine. As you go to smaller scales, you find that the results are not so great. I mean, in the sense, it's more chaotic, more noisy. The system is more noisy, more difficult to predict. And we are looking at active break spells of the monsoon. we know that rainfall during a monsoon is never uniform. We all know that there are periods when for days and days it rains heavily, and for days and days again there is no rainfall. So these we call as active spells, and we are basically looking at this region. When we talk of active and break spells, is what we call as the monsoon core region. And during weak spells, rain is confined to the foothills of, let's say, here, Himalayas, some parts of Western Ghats, and maybe parts of Northeast India. And it's important to predict it because, a farmer would like to know 15 days or 10 days in advance whether he's going to get rain in the next 10 days or 15 days. So that's where prediction of the active and break spell is important, or also for reservoir operation. They know whether they should kind of release that water or they should kind of store that water. So for both of those and for many other areas, it is important to do these active break spell forecasts. And it's also known, this is actually a work from Rajivan, that during drought years, you have long periods of break spells, and active in excess years, you have long periods of excess rainfall. So it kind of also modulates, the active break spells also modulate the strength of the mean monsoon. Okay, I'll skip this, and this is the technique we used. We also tried LSTM, CNN, and I think even used KNN, but I think the best we got was from CNN. And since we are looking at daily rainfall is noisy, we try to kind of do a 5-day prediction averages, kind of with a moving window. That is, on every day we take the next 5 days, previous 5 days, and then we do a forecast for 5 days, and then kind of keep moving the window. And these are the geographical regions that we used. We didn't use the entire global data as previously. Of course, what we were trying to do was with just a simple PC. So obviously, this was in the late, around 2018 or 2020. Yeah. It's a difficult question. I mean, we assume that, very long-term effects may not do it. But we also know that the large kind of a pattern, the envelope that happens, it has an impact on the subseasonal scale, which is why we said, okay, there's a localized envelope, a region where we are going to do. In addition to, we know that, okay, usually if there is an El Nino or a La Nina, that has an impact. And also the high pressure region in Mascarene region, that can have an impact on the strength of the monsoon. We actually try to do up to 15 days, but at any time we are taking kind of 5-day, in some sense, an average, which is a kind of a moving window. That is, I start at 15 days, but I start from 1 day, and then I kind of keep for 2nd of June, 3rd of June, so on and so forth. I keep doing a 5-day average and keep moving that window. Because daily data is much more noisier. So that's why we tried doing it. There was no signal coming easily, so we thought we'll do with this.
At which level? Or all the levels?
I think we used both, if I remember correctly, it must have been 250 and 800. So that you get the 200 and 850. Basically to kind of get the overall large scale circulation pattern also into it. So these are the results, and it's a busy picture. Basically, we try to compare it with the only existing model that was there at the time, which is a self-organizing map. And we could find that the results were comparable, and we get better skill also for break spell as compared to active spell. So that's the signal we are getting. And this is not my work, but a recent work from US by Bach et al., where they have combined the coupled model forecast, CFS forecast, and kind of projected it onto MSSA and tried to do a prediction. And they are saying that there is an improvement in both temporal correlation for monsoon region and India. And these are the increases that they are trying to find, which seems to be very impressive. And maybe some people can look at it, but it's a fairly complicated technique if you want to use. You have to first develop an MSSA technique, which could be with data, and then again kind of project it onto CFS forecast, and then kind of take it next 40 days. But what they are finding is that it's able to kind of get a very fairly much better forecast. This is about the best forecast I'm seeing at the intra-seasonal scales. Okay, so I'll move to the next part, which is prediction of heat stress. It's a work under progress. And I don't think I have to tell you that heat stress is a major problem. Just looking at this figure, you see that the country which is most affected by heat is just stands out from this figure, which is India. And so obviously, it's going to be a major problem for us. And I'll skip the other details. And this is a work which we are doing. I'm doing this with, it's a work under construction with Art Park, which is the startup hub of IISc, and it's partly funded by BIRAC. And IMD, IITM, and Government of Karnataka, the State Disaster Management Group, all of them are kind of working together to develop this. Basically, right now, we are just looking at for Karnataka. Later on, we want to see whether we can kind of extend it to other states also. There's already kind of discussion going on to do it for Tamil Nadu. And maybe if there's interest, we can do it for the entire country. So this is the overall picture. We can say the co-innovation plus co-implementation, where you have like union states, monsoon mission, NDMA, etc. The data is coming from different sources, which is the KSDMC, ERA, which is the European Reanalysis, IMD, etc. And the climate input is coming from basically IISc, IMD, and IITM. And it's a kind of where we are not just, right now we are just only looking at the climate part of it, but at a later stage, we would like to kind of combine both health and climate together, get information and kind of convert that heat. Well, basically, we may say that from climate, you will say whether there's a likelihood of a heat wave or not, and how that kind of can be translated as a heat stress for different sections of the society, which partly Dr. Mahapatra also talked of in his one of his previous, in his talk. So that's what we would like to do. But at this stage, right now, we have done only the climate part of it, just converted into some initial heat stress with existing whatever information that we have. Later on, we actually want to do a kind of, do it because we know that what the kind of heat stress they are talking of is kind of, they are doing it for US regions, they'll say some definitions which may not be relevant at all to us. They'll say that, okay, 30 degrees is high temperature. Well, I'm very happy when it's at 30 degrees, but for them it becomes a major problem. So we are kind of trying to get our own definition of heat stress. And this is a work with the various people. There's a huge group which we are kind of working with, which includes people from health, like Dr. Kaur is an expert in public health. She works at the IISc Center for Health. And of course, Dr. Soumya Swaminathan, whom you're already familiar with, former Deputy Director General of WMO. And of course, Rajiv from IITM. And of course, many others who are listed here. So this is the current status that we have. Like, if you look at, you have conventional models which give you 3 to 5 day lead time. You get, say, a signal, but the signal rapidly deteriorates when it comes to heat stress, especially at the district level. So heat wave is only based on temperature. And so we are looking for risk classification based on temperature. But if you look at, let's say, even a state like Karnataka, which, I mean, climatically, it might look very comfortable place, but then if you're looking at, it has 3 zones, which is kind of, and it's kind of representative of the entire country if you want to look at it. You have a very kind of a comfortable place where I should say that I live, which is around Bangalore. Then you have the northern place, which is one of the hottest places in northern Karnataka, hot and dry. And then you have coastal Karnataka, which is hot and humid. So the 3 major kind of, if you were to build a model which kind of address all these 3 regions, then it's very easy to kind of, once you build this, you can do it for the entire country, because these are the 3 major kind of things that you would be looking at when you're looking at the entire country. So it becomes in some sense a good test bed for us to do this work. So what we propose to do is AI-based forecasting, hopefully 10 to day, 12-day lead time at sub-district level, and give a heat stress which includes temperature, humidity, wind, radiation, etc., and risk classification that is a health risk and its communication. So it's the kind of an end-to-end kind of a solution with a dashboard, interactive dashboard kind of a thing, which we can do that. This is the approach that we are taking. The top part is what we have done. We start with some initial condition, which could be from reanalysis or analysis, because we are now looking at real time, or it could be forecast at a station data. First, we are trying to use just existing AI models like GraphCast, Pengu, Fuxi, and Pango Weather, etc. At a later date, we want to develop our own AI model just for, let's say, related to heat stress kind of a thing. Then we do corrections of it. We know that all models will have biases. So currently, we are using kind of a quantile correction. Then we may use an individual model, or we can use an ensemble of models, which could go into a model evaluation. At that point, you could kind of start calculating the heat risk. And currently, we are using existing definitions of heat risk. We would like to take data from primary sources, kind of create new health risk data, and kind of feed the entire thing into a targeted heat risk board. So these are the models that we have used right now. These are the forecast net, Pangu, GraphCast, AIFS, Fuxi. And we are also kind of comparing with, the comparison with is with the European Center, which is always considered the gold standard. If you can do better than them, then you are in business in some sense. So these are the variables that we have compared it with. And here is the comparison. This is for the Indian region for April and May, which is where heat risk is a problem. So this is the IFS IRIS, and these are the individual members. And this is the RMSE, root mean square value, as it changes with time. So you can see that they are doing better or comparable to what you get with the European Center. Okay. The best thing is all these forecasts, we are now kind of generating with just a single kind of a GPU-based system. So every day, you don't have to wait for anybody else to give us the forecast, except whenever you get the European forecast, you can do a comparison with them. But otherwise, on your own, if you want to do a forecast, you can just generate it within a matter of few minutes, a forecast of skill which is comparable to that of the European Center. So that's the advantage that we are kind of getting. Right now, we are using the European initial analysis, because reanalysis will not be available in real time. It has a 5-day kind of a lag. So we use the initial condition which European Center gives you as the condition. I think it's within a few hours you get it. You should be able to get it. That's what I'm finding. No, it would be different, because reanalysis, what happens is even on a delayed mode, let's say some satellite data is coming, it hasn't come in the time, they want to do a t equal to 0 at some time. Whatever data comes in, they create that condition, and that goes into their forecast. So in a sense, it's a fairly apple-to-apple comparison, because you're using the same data, whatever data they have used, and then we are doing a comparison of the same forecast. If we were doing it reanalysis, it's like there might be more data you would have gotten. But if you're trying to do real time, there's no way you can do it the reanalysis. Yeah, so that's why we are using the analysis, the t equal to 0 forecast, which also we are taking from European Center. And this is the scorecard. The top is the physical model. This is the IFS high-res ensemble, Pango Weather, GraphCast, and Fuxi. And the one in red says that, okay, it's doing worse than the European Center model. And the one in blue, darker the shade of blue, it means that it's doing better. So, and if you look at which is the best model for which day, on day 1, you're getting GraphCast. On day 3, again, it's GraphCast. As you go further, it is Fuxi, which kind of dominates. So if you want a long lead forecast, Fuxi could be a better model as compared to GraphCast, or let's say even ECMWF. So this is some detail of bias correction that we have done, because we know that all models have bias. So we have kind of done a bias correction of the temperature. It's nothing, at this point, it's nothing rocket science. It's simple quantile correction that we have done. But it seems even that simple correction that we have done has kind of improved the forecast significantly. Okay, so this is a sample of a 10-day forecast that we have done for the Indian region. This is not a qualitative comparison. It's just a quantitative picture to say that, okay, we can get reasonable results up to 10 days lead. And these are the forecasts that we are doing it for Karnataka. As I said, it's a very heterogeneous region. So like if you're looking at coastal Karnataka, it's humid, southern Karnataka is hot and dry, and southern Karnataka is fairly comfortable. So this is the actual dashboard. I'll just quickly go through it and see if we can. Yeah, so this is the actual real-time kind of a view of a current forecast that we have done, which is kind of being displayed. And you can look at various districts or various sub-district level and see what is the kind of heat health you're looking at. Right now, you're looking at a district called Belagavi with a sub-district called Chikodi. And this is the area where it is. And nothing much to say because the time of the year is fairly comfortable. So all the risks are fairly low in this case. Okay, where has it gone? Oh, I mean, it had pulled up a website, so now I have to go back to my original talk. Yeah. So you just have to go to this one. Yeah, I think yeah, this should be fine. नहीं ये तो फिर से वहीं पे पहुंच गया. Just yeah, PowerPoint slide. Yes, please. Yeah. Yeah, that might be. Sure. Just full screen कर. हाँ, वहाँ कहीं पे भी रोक दीजिए. हाँ, that yes, that one. Yes, please. Full screen. Oh. Yeah. Okay, so I think I'm running out of time. If I'm running out of time, please tell me. Otherwise, you know, we professors have a tendency to talk and talk. So you can stop me at any time brutally in case I'm done. Okay, so these are the expected outcomes that we are planning to look at, and this is a predicted temperature data set that we created using and kind of also used AIFS for that. For some reason, it's not. Yeah. So we have taken data from KSDMC, which has about 1,000 weather stations, and hourly humidity and temperature data. These are the details, and then we are trying to first do a downscaling of it to 10 kilometers, and then kind of also use the AIFS data, combine it to give a forecast for Karnataka. So I think I'll stop here, and which basically what we are trying to do is the temporal features come from the AIFS, the spatial feature comes from the observed data that we are getting it. We're combining that through a UNet. These are the details of the UNet architecture. So I think I'll stop here and I'll take questions if there are. Or
great talk. Any questions to Professor Ravi?
The heat risk? Will the heat risk model be open sourced, or is it like?
Yeah, everything that we are trying to do, even generate the data, we're planning to put it on open source. That's our policy. Yeah. As of now, it's still under construction. If I give you, you might curse me, but yes, we want to make it open source, both the data as well as the model also. Model should be available whenever we have kind of reached a kind of a good level, we'll put it on GitHub and you can take it. And the data would be available from the art park. They have a site, archiving site, so we should be able to give it to you. Okay.
Does that part with the covering for here, we have state data and the AI.
Huh.
You mentioned downscale. What exactly are you using for the downscale?
Okay. First is, I mean, the AIFS comes at about 25 kilometers. And what we would like to do is that, and we have station data. So we kind of create, there are two steps we are doing. First is we create a station data, which is basically we are using angular distance method. Unfortunately, I have run out of time, otherwise I would have discussed it, but just a simple angular distance kind of a gridded data set. And now, based on it, and also the data that you are getting in real time, you are going to train with that and at AIFS and finally kind of do a downscaling on it. Okay, and so that you can do it at 10-kilometer resolution or even finer if you can. Of course, station data is at much finer scale. Right now we are doing a downscaling at 10 kilometers. So we are going to downscale the forecast itself to 10 kilometers. So it's going to use AIFS. Tomorrow I can use any other model also. That should not be a problem at all.
The question about the earlier part of the talk, you studied like testing teams around the world, which are impacting India.
Yeah.
So what's like the time scale of these? I think they're called teleconnections from now.
Yeah.
So like what's the, if something happens, but it goes in August, then it is back in India in like September. Like is there any study of time scale of?
Right now, okay, what we have done is for the seasonal monsoon. So we have taken data only up to, let's say, 1st of May, or because we are going to do it from June onwards, June to September. So any data that we take up to May, which could be up to, let's say, as I said, from August of previous year, if you take sea level pressure, it seems to having an impact on the monsoon. So it's basically monthly data that we are looking at. We are not looking at any finer scale data. Yeah, because we are looking at seasonal scale, so, and we are looking at the 4-month pattern.
Seems to be some online questions, sir. Which ML model is used for training? Which ML model is used for training?
It's a unit kind of. You mean for the downscaling or for, can they say whether they are looking for downscaling or they are looking for?
Possibly for downscaling.
Yeah, I think it's a unit. Previously, coarsening the data, we have used only angular distance, like whatever AMD does, that the same technique we have used. We have used a combination, I mean, we tried the combination of them, but somewhere I have it. But
if you're online, you can just unmute and ask.
Okay. Sure.
So,
yeah,
I was
so it's basically unit is what we are using it for the final forecast at the, where we combine AIFS with the gridded data. Gridded data we are doing with angular distance.
So you said that you are using the operational SMWF
T equal to
analysis
0, yeah.
that you get free or you purchase?
No, यार पैसा नहीं है.
I see.
No, we found out a place where they kind of put it
Okay,
up, so
so-
we are kind of taking it from there.
It's not a straight path.
No, it's fairly straight because we're not doing anything illegal or any illegal site. So I'm sure it's available somewhere. One of my enterprising students or my colleagues found out that they could do that, so they have done it. Yeah, sure.
First thing, maybe we should take that link from you. To get the analysis data from ECMWF, we should also get the link from you.
Sure. I mean, you just write to Vaibhav. He's one of the collaborators with me. He'll be happy to share that link with you. I mean, we are trying to make all the data open source. So nothing, it's not my data. So if it's available to me, it should be available to you. Not a problem at all. Yeah.
So I had a question about the monsoon model, because you started initially by pointing out this asymmetry between the wet years and the dry years,
Yeah.
and how the responses were, right? Does the model prediction accuracy also show some kind of an asymmetry? Like, have you looked at, like, whether it's equally confident in predicting a drought year as opposed to predicting a wet
Okay.
year?
Yeah, I got your point. The problem is that the testing data set is fairly short, right? We did from 2010 perhaps to present, or 2000 to 2010. So there are not many droughts or excess years. There were no excess years. Let's say till I think 2019, The previous excess year was in 1994. After that, the next excess year was in 2019.
I mean,
So there were no excess years in between.
we could look at the training data as well, right? I mean, because even in the training data, it's not necessary that it has 100% accuracy on
Sure,
every
we could
training
take
data.
a look at it, absolutely. But I mean, usually, training is like, they'll say, yeah, you have fitted everything. So it's a kind of a curve
Actually,
fitting. So
that's not the case. I mean,
yeah, if you want for analysis, yes, we can use training data, but we have not used it. Sorry.
Just curious.
So just the accuracy is whatever we found, the mean error is what we have kind of
Well,
reported.
yeah,
Okay.
using the TG archive, TG archive in
Ah,
Istanbul.
yeah.
You can also try the hindcast, right? Because in TG you get all the archive right from.
Sure, we can do that. Yeah. I
So
mean,
then
that's
you
what,
can- so
like
currently you
whenever
can-
we used a comparison with HF,
Yeah, so
that
currently
we
you can-
use from TIGI data.
Yeah, so currently you cannot compute the anomaly, right?
I can.
How? You don't have model climatology, right?
Yeah, I have.
How did you
I have
generate
done the hindcast for all the models.
using which initial condition?
I mean, that I'm using ERA.
So what I'm telling you,
I mean,
reanalysis, so to make it apple to apple, to make it.
yeah, if you want to redo it that way, but I
yeah,
think we
because
did try with the peak.
your current forecast is based on operational analysis.
Yes.
Hindcast is based
Which
on
would be worse than, I mean,
reanalysis.
actually it's a worse comparison because the
Yeah.
operational analysis is less
So
accurate as
to
compared.
get the zero UTC TG data actually
Yes,
is the
we could
operational
do that.
analysis.
Operational
So you can
analysis.
use the TG zero,
Sure,
T0,
we could do that.
and then
But
it will
it's
be-
already trained, like the model is already
Yeah,
trained.
I got
So
it.
we are using their training weights and just doing a forecast
Yeah,
based on the ERA
I agree.
analysis. Yeah.
But it can be redone and
It could be redone.
be-
That's not, I mean, once you have the training weights, it's not a problem.
yeah.
Making those training weights is the problem, and that's where we need huge
Right.
computational resources. Yeah.
Very good. So sort of time. So let us give a big hand to
Thank you.
Professor Ravi. I hand over the mic to.
Sure.
Oh, sorry. So one moment, Sandeep, you give. You invited him.
There's no pictures here, but thank you so much.
Thank you. I hand over the mic to Professor Ravi.
I can tell you one thing about CV, about Sovimal. He was a student, and I was